Okay, people, let's get started. Today's about the food production system and what's going to happen to it over the next 30 years, and why food production is a nexus problem that interacts with the other nexus problems. I showed you last time that the distribution of land on the earth is that we've got about 38% of the land area of the earth is technically agricultural, with the land that is technically pasturage, twice the land that is cropland. There's this big bolus that is forest, and the forest is located primarily either in the far north, that is the circumpolar boreal forest across Canada, Alaska, and Russia, or it's located in the tropics. There's a very large hectareage of forest, 1 billion hectares of tropical forest that remains. More than half of it in the Amazon, but substantial amounts in Central Africa and in Southeast Asia. And the rest of the land is basically unsuited to agriculture. It's desert, rock, tundra. It's unusable. And you can see that urban land is just a little teeny snippet there that can be ignored for our purposes here. As you know, the tropical forests are already reduced in size enough that there's a substantial threat to the biodiversity in them. And so this is why I say there's a zero-sum game for the nexus problems when it comes to the land area of the earth. If you look at the grazing land, the grazing land consists of, these are millions of square kilometers. That's also the same as billions of hectares. If you, that is 10, that divided by 10 is billions of hectares. So there's about 1.5 or 1.6 billion hectares of cropland, and there's more than twice that of grazing land. But the important thing to note here is these colors represent how wet the grazing land is. So this bunch of grazing land here is like if you've ever driven across the United States and looked out in Arizona, and there's like 1 cow for every 2 square miles. That's technically grazing land, but you couldn't do anything else with it agriculturally. All right, you can get a little bit of forage off of it. It's technically called grazing land, but it's not possible to convert that in any way, shape, or form to cropland. And if you were to abandon it and try to, say, store carbon on it, the productivity is so low that you wouldn't end up with very much. You'd end up with a shrub steppe with a small amount of carbon stored in the ecosystem. Whereas down here, this is rain-fed, wet pasturage. Think of happy-looking dairy cattle, right, in Europe or in Wisconsin. And if you could, in fact, grow crops on that land, and if you were to abandon it, it would very quickly revert to forest that stored, 100 tons or 200 tons of carbon per hectare eventually. And so this land, which is roughly the same area as the cropland of the world, is in fact an interesting resource that could be used for cropland. It could be used for grazing land. It could be used to grow energy crops. It could be used to store carbon, all right? So all of those things. The cropland itself, as we'll see, is split in use between human food production and animal food production. So a lot of the cropland, it turns out, is also now producing animal feed. So a shocking amount of the land area of the world goes into feeding animals, not into feeding people directly. So these are the agricultural lands. This is not surprising, I'm sure, to anyone. This goes from 100% cropland here to 100% pasture here. And the pasture lands tend to be drier than the croplands. But even in places where you sort of think about the land being some mix, like in Europe, it's kind of 50-50, right? Cropland and pasture, it's kind of an intermediate color there. And then there's a substantial fraction of the land surface that is forest in those locations. Again, the threat to biodiversity today is 3/4 agricultural, right? It's not climate change yet, starting to be. A couple of species have been lost to climate change, but the vast majority, the problem itself today, the reason there's an Endangered Species Act and that sort of thing, is primarily agriculture. Now, if you ask, where do agricultural lands come from? Well, it's not too surprising, really, that if there's pressure on the food system, it's not coming out of pasture. Obviously, new agricultural lands, croplands can't come from pasture. Agricultural lands have to come from non-pasture, non-cropland. And so where are they going to come from? Well, they could come from forested lands, or they could come from desert and that sort of thing, but they can't come from desert because the productivity is low. So the origins of new agricultural lands are almost all forest. Some of the forest is labeled as disturbed. It's previously cut down forest, but it's not too surprising as human settlement, for instance, in the Amazon, marches into the Amazon. First thing they do is high grade the timber out and sell it. Next thing they do is cut down the timber and convert it into cattle. So a lot of the forest that is disturbed and converted into agriculture itself was first converted into disturbed forest from pristine forest. But you can see the story here is one in which it's forested land that is going to slide into cropland and pasture land if, in fact, we expand the agricultural land base in the world. Now, this is really the most important figure, I think, in the whole business. It comes from a paper by a guy named Dave Tillman, who's at the University of Minnesota. And he's not an agricultural scientist. And it's surprising that these graphs really hadn't been made in a simple way before. And all Dave did was he plotted the per capita GDP versus the per capita caloric demand, how much food the people consume. And he also did per capita protein demand. And to make the data intelligible, he divided them into a bunch of different countries, all right, different groups of countries that he thought made some sense as groups of countries. Some are the most developed countries in the world, that is group A, and some are the least developed countries in the world, that's group G. To be honest, this categorization, pooling together the companies, does obscure important cultural determinants of diet. And I'll get back to that in just a second. So what he did was he put a dot for each year from 1961 to 2003, all right? A dot for each year. And so these represent a time series of growing per capita GDP in these group A most developed countries, for instance, starting in 1961 and ending up in 2003. And so for the rest of them. Now, the thing that should jump out at you is that they're all doing the same thing. As people become more wealthy, what they do is they consume more food. And in particular, they consume more protein. This appears to be, by these data, locked in cross-culturally. It's like it's deeply embedded in the human DNA or in the human psyche, or is somehow common to all cultures. Now, with that said, if you were to specifically, and I've done this, right, cull out Hindu countries. So cull out countries in which Hinduism is practiced, majority practiced, and people's diets are actually determined by Hindu beliefs. The protein fraction is off scale here, falls way down lower. And that's because they aren't consuming animals as they become more wealthy. So so although this looks like biological determinism, like just about everything else that humans do, there is a huge amount of nurture that's possible here. And so Hindu cultures, if you just plot, and you can get these data are easily available from the FAO, if you just type capital F, capital A, capital O into Google and look at their data, you can pull these data out and you can do it for yourself if you want. But I really find this fascinating because usually when you see something like this, it's a log-log plot. And log-log plots make everything look as though it's going along a nice mathematical relationship, even when it isn't. I one time took an elephant and turned it into dots around the perimeter of the elephant, and then plotted the dots on a log-log plot with the elephant sort of looking up, and it looked like a perfect straight line. Okay, so the point is that, I mean, I did that to point out to people that you can really make things look like there's a strong relationship with a log-log plot, and it's because, you know, with a log-log plot out here, there's a huge difference between the tick marks, and then and down here, there's no difference between the tick marks, and so this thing can be like a cornucopia of scatter that collapses into a straight line. But these aren't log-log plots. I mean, these are just numbers, and so this is really a striking pattern. Okay, yeah. There you go. Okay, they're all Tour de France racers. Right? So that's, in fact, is an excellent question. Why is this 8,000 calories? Okay, and so what's going on there? And the answer is, what Tillman did was he took the total food production, the yield ratios that get into the marketplace, and divided by the number of people. That's what he did. And the answer isn't that they're all Tour de France racers. There's a few who might be eating those kinds of calories. Is anybody out here is such an endurance athlete that they eat 8,000 calories a day? Yeah, there's one, right? Yeah, so it's possible to do, but you really got to work at it. Okay, you've got to want it. All right, and so the answer is meat. When you do that, what you're obscuring is the fact that most of the agricultural production is in fact going into animals. And those animals are keeping, if they're cattle especially, but even if they're chickens or pigs, they're using that energy to keep themselves warm. And they're only able to effectively transmit 10% of it into humanity again. And so that's what's going on here. It's that it's all meat. That's the protein demand. So what you've got there is a growth in calorie demand, which is not that people are eating more, it's that they're eating more meat. And so it's amazing that there's this cross-cultural tendency to want to eat meat, all right? That people really want it. The kind of meat depends on the culture. In China, pork is like the big thing. In the US, obviously, historically, it was beef. Beef made you rich, right? Meant you were rich. And you can see here that if you take kilograms of feed per kilograms of live weight, it's 10x for beef. If you actually look at the edible parts of the cow, you can go from edible feed to edible cow, and it's 25x. All right, so you lose 90% of it when you're growing a cow because the cow has to keep itself warm. And you lose the rest of it because of the stuff that it didn't burn to keep itself warm. It made a lot of it into bones and rumen and stuff that humans can't consume. Pork is better, 5 and 9.4, but still crazy land, right? Chicken's better still. When we get down to carp, it's a lot better. And the reason is that carp don't try to keep themselves warm. They adopt the temperature of of their environment. All right, so they're not homeothermic, and they aren't just burning energy to keep themselves warm. Milk is also surprisingly good in terms of the conversion. But on the other hand, yeah, so I mean, it's amazing, really. On the other hand, that doesn't include the energy it took to actually build the dairy cow. That's once you've got the dairy cow, right? How much extra you got to feed it if it's lactating. So this is the story of meat. Livestock production is a multi-trillion-dollar business that employs more than 1 billion people globally. But surprisingly, it's only supplying some, minority of the global calories and the minority of the global protein still, because there are a lot of poor people, right, that don't have, they would want to eat more if they could, but they're too poor to eat more, right, as that relationship said. But globally, 62% of crop production is going to humans and 35%, so a full third, yeah. That's all of it.
Would milk be?
Yeah, but milk is a small fraction of the total, right? So that this is goats, sheep, pigs, cattle, and chickens. Okay. And so a third of the crop production is going to animal feed. Only 20% of cropland grows animal feed. And what that should show you is that animal feed is actually grown on high productivity land. And it's because you got only 20% of the cropland, but 35% of the calories, right? Of the protein, of the production. And so what that represents, you should think of the corn-fed beef. So in the US, so much of beef production, a lot of the cattle start as grass-fed for about a year or less than a year, and then they're shipped to a feedlot where they're fed corn, and the corn itself is raised on some of the most fertile land on earth, right? And so that's what's going on there. All right, so the point is that this is the story of animal production. Now, as people become, this is another like Tillman plot, but it's significantly messier. But what this is human food is in red and livestock feed is in blue. And this is per capita GDP, okay? And so what this shows is that as a country becomes rich, the agricultural lands within it shift from red, which is human food production, to livestock production. So there is majority livestock production in rich countries, agricultural land, all right? And it's the high value product of an agricultural system is meat production. So as people become rich, they demand more meat, more productivity goes to meat production. And that's what is overwhelmingly causing the growth in food demand, not human population growth. The growth in food demand, the 60% increase in demand that we expect to see over the next 29 years will be caused by people becoming more wealthy, all right? And shifting their diet to meat production. That's going to require more feed to do it, unless something changes technologically or culturally or behaviorally. And the fact that the relationships in the Tillman plots are so tight, despite being cross-cultural, probably indicates that it's difficult to shift diets. There have been decades of attempts to shift American diets away from meat, away from beef. And it's shockingly little progress. Little bit of progress in getting people to go to chicken instead of beef, but no progress at all. I mean, sure, there are more vegetarians than there were, right? There are a lot more vegans than there were, but it's still a tiny fraction of the total population, right? And so the historical expansion of crop and animal production was driven by population growth with diet shifts related to wealth, all right? And what's interesting, I think, is that, and so, just about every category here, these are different crops, and these are different groups of animals, has been exploding through time to meet this increased demand. We've had a period of rapid population growth, which fortunately is stalling now, so that now most models predict a peak population size for humanity by mid-century, right? And but we've had tremendous increases in wealth that have driven the growth in production. And historically, most of the needed production was met by increases in the yields of our agricultural system, not by increases in the amount of agricultural land. So we've got a track record of squeezing more and more production out of the existing land. And the data indicates that we aren't done yet, okay? So we can keep going. Now, most of this change, most of this higher productivity through time was caused by increased application of nitrogen and phosphorus fertilizer, and also increased application of pesticides, both of which have significant negative environmental consequences, but they have fed humanity, all right? One of the primary reason that we couldn't stop using fossil fuels as a species right now is that if we waved a magic wand and stopped it, most of humanity would starve to death. And most of humanity would starve to death because fossil fuels are used to fix atmospheric nitrogen and make nitrogen fertilizer. And without that fertilizer, the yields would fall. And there literally wouldn't be enough food on the planet to feed even the majority of extant people. All right, it would be a mass extinction event. Billions would starve. So we're really in a box here, okay, which is why the climate problem and the energy problem is so important to solve. All right. Okay, so it's pesticides and fertilizer. And the bad news and the good news is that the sub-Saharan Africa has lagged way behind. And the reason it's lagged behind is that in the yield growth is the low application of fertilizers and low application of pesticides. So we know exactly what we do to get agricultural yields up in Africa. So there's a lot of ground we can still make here. This is fertilizer application. The top graph is nitrogen in the upper left, and in the upper right is phosphorus. This is per ton of yield application, nitrogen and phosphorus. And this is excess. Farmers dump too much. They dump more than they need. And a lot of it runs off into the water, which wastes money, but it's still what happens. And the excess nitrogen and phosphorus, you can see there are heavy concentrations for nitrogen in the northern Midwest in the US, across India, and in temperate China. All right, phosphorus, tremendous over application in the Gangetic Plain, and again in temperate eastern China. And this, of course, has negative consequences because it gets into the rivers. And one thing you've probably heard about is shown here in a satellite image. And what that is the oxygen levels in the ocean off the Mississippi River mouth. Okay, so that's Louisiana. New Orleans is right up in here. And the Mississippi River comes in and discharges, and it's discharging that excess nitrogen. And the nitrogen causes a phytoplankton bloom, and the phytoplankton gobble up the nitrogen because they're nitrogen limited, and they take CO2 from the atmosphere, and they make more and more of their bodies, and they consume more and more oxygen when they do it. All right, and especially when they get mixed into the deep, consuming oxygen, and they make the deep actually anoxic, consume all the oxygen so that if a fish swims in there, it dies, all right? And these anoxic substances, what happens to a temperate lake if it gets too much fertilizer runoff? It turns into a stinking cyanobacterial, green, matted, mossy looking mess. And if you disturb the water, it smells like hydrogen sulfide, and smells like hydrogen sulfide because there are anoxic bacteria down there that are metabolizing that way. Same thing happens now in the ocean at the mouths of most of the major rivers that are near agricultural systems. And this is a global problem. We have actually no idea what the global consequences are, but it is something that's alarming to anybody who's watching the progress of this. Now, although agricultural land has also expanded in addition to these yield increases, these expansions are surprisingly small. This is a complicated graph you can look at. It comes from the supplementary material in the Foley paper that's in the reading list. And the thing that you should take a look at is just this column here. This is the full change from 1985 to 2005. That was an era of big change in the food system, 20 years long. And these are the percentage changes of land area that goes to agriculture. And you can see single digits there. Like 3 is a big number. And so the point is that although this looks like a big deal, it actually isn't. Not very much land has been converted to agriculture. If you take a look at it as a total, yeah, a lot of, millions of hectares have been converted from primary forest to agriculture. It is a fraction of the total land. It's actually not a very big number, okay? So 20-year change here, of just a few percentage points. So you can look at this at your leisure. Globally, it's 3%, but that includes cropland, the cropland change, and a pasture change there globally. So it's a surprisingly small impact for 20 years. Now, the change, the mix so there's 2 factors that are causing an increase in productivity of our agricultural system. One is increased production per hectare. And I'm sorry, one is increased production per hectare, and the other is increased numbers of hectares. And what this graph shows is it breaks the different crops down into which of those 2 factors has been responsible for the productivity growth and production of the agricultural system. And so you can see that, for instance, wheat and rice, to some extent maize, have all increased, not because the amount of land area that's devoted to wheat and corn and rice has increased, but because the amount you get per unit area has gone up. So this is, crop breeding and pesticides and fertilizer and stuff like that. In contrast, sunflowers are all from, nobody's improved the sunflower yield, right? But instead is that there are more sunflowers now than there used to be. And soybeans are really dominant, a land area story, not a productivity story, all right? So that's the one really big crop. It is almost all land area, all right? So the story is both are important for some crops, particularly soybeans. The amount of land area devoted to it is important, but overall, this is a story of pesticides and fertilizer and crop breeding and that sort of thing. And increasingly, it'll also be the story of genetic engineering and crop varieties that are produced by technology. Okay, so food demand's going to double from 2012 to 2050, which means a 60% increase from today to mid-century. You can use some projection of population growth. This is a UN midpoint projection. You can use Tillman's relationship here between per capita caloric demand and GDP, and you can use economic models of GDP growth per capita and turn that into a forecast, turn those three things into a forecast of how much food we're going to need. And that's where these numbers come from, okay? So it's population's growing, GDP is growing, and food depends on GDP and population. Per capita food depends on GDP, right? And per capita, and the number of people depend on population growth. And so when you do that, you get pictures like this one from Tillman's plot, where he has group A countries here and group G countries here. And what's going to happen with per capita GDP? This is 2000 up to 2005 when his analysis quit. And this is the projection forward, projection for the calorie demand and projections for the protein demand. So these numbers that we're talking about are the result of demography and economics and then empirical relationships between protein and calorie demands and wealth. I don't think we need to look at that. You can take a look at it. It's projections for growth in meat demand. The important thing here is that total consumption in developing countries of meat here from this study, but from all of them up till about 2 years ago, were just explosive, tenfold growth expected from 1980 to 2050 in meat consumption, and a threefold growth or a 2.5-fold growth in meat consumption from today to 2050. For developed countries, much smaller, but the developing world, as it got rich, was just going to eat meat all the time, and that was going to then drive this massive increase in food demand. However, 2 years ago, and I think it's a couple of the meat substitute companies went public and made a whole bunch of money. So Impossible Burger and Beyond Burger, I think. And all of a sudden, the analysts started to take this seriously, and the stony-hearted business analysts who are just looking at trends for investors, and this includes Bloomberg and Statistic and a whole bunch of them, started to look at the growth in meat substitutes, and they thought, there's no way to stop this. They're going to be cheaper to produce, and people apparently like them, right? And so how do you stop it? And the answer is they decided you couldn't. And so 2 years ago, this is the first time we had a prediction, whereas instead of meat consumption going up and up and up and up, what was happening is that meat consumption was going down. That's conventional meat, is this purple-ish area, pink purplish area. And it's because of the growth in both cultured meat and meat substitutes, okay? And so this is really a fundamental change. So now think in your head of what we've learned and how this might be impacted. We know that the amount of like mesic, that is wet pasture land, that is devoted to animal production is already of similar size to the croplands that we have. Remember those green bars versus the total cropland, billions of hectares. And that land, if you didn't need to produce meat on it, could be used to grow trees to store carbon. It could be used to grow crops if you wanted to. It could be used as a biodiversity preserve. It could be used to grow energy for biofuels. All of a sudden, this appears to be handing humanity a key to loosen the zero-sum game that you were otherwise facing on land area, all right? And it gives you a big number, like 1 billion hectares to fiddle with, okay? So this is, I don't think, if you look at the COP26 discussions, nobody's talking about this, but I think it's a big story. So I think you're going to discover that this is one of the big gifts you will have been handed, your generation, to actually solve the carbon problem. It's 1 billion hectares of rain-fed land that you get to do something with, right? If in fact these predictions about what's going to happen to meat substitutes are true. And I think they probably are. Okay, so 2050 food demand, population grows a bit. Per capita GDP grows a lot. Meat demand, I've got a question mark here that used to say triples, but 2 years ago from now on, it's, I don't know, right? But if I had to guess, if I had to give you my dominant viewpoint, I think this number would say halves. And food demand increases not by 60% now if meat demand halves, all right? Meat demand halves. All of a sudden, you don't need to use that land to keep cattle warm. You can use it to feed people, or you can use it for other things. And all of a sudden, food demand does not grow by 60%. All right, a much bigger story than all the other parts of the agricultural story put together, just in terms of raw numbers at sort of nexus global scales. Okay, if yield improvements track regional business as usual, from 1965 to 2005. So if, in fact, there wasn't anything special that happens to our agricultural system, then, in fact, with the growth in meat demand from the developing world, we will have need for more agricultural land. And business as usual would carry us to 1 billion hectares of tropical forests converted to cropland. All right. So if you take a look at business as usual stuff from 20 years ago, we're carried into a dark place where instead of getting an extra 1 billion hectares to play with, we use an extra 1 billion hectares, and that's got to come out of forests. And most of those forests are going to be where the demand is, and that means tropical forest. And so this would cause a mass extinction, right? We already saw this would cause the loss of something like half the species on Earth. But it would also cause climate difficulties. So this slide shows how much carbon is stored. Now, this is tons of carbon, not tons of CO2. To get tons of CO2, remember, you have to multiply by 44/12, right? 3 2/3. So tons of carbon in vegetation in a tropical primary forest. There's about 200 tons of carbon in a hectare, which is 100 by 100 meters. It's a little over 2 acres. 100 by 100 meters, you've got 200 tons of carbon. And there's about 100 tons below ground in the roots and in the soil. Okay, so that's above and below ground. If you look at a grassland, it's 5 tons above ground, 150 below ground. A pasture, especially a tropical pasture, is like 125 below ground and 9 above ground. The 9 is because there's a lot of bushes encroaching in the pasture in addition to the grassland. And cropland is depauperate from turning the soil over and aerating the carbon in the soil. A lot of it gets smoked off, it decomposes and goes into the atmosphere. So there's 75 versus 2. Now what happens? If I convert primary forest into pasture, I lose 191 tons of carbon above ground. See that? And I gain 25 of it back, all right? So that means that I've got like 166 tons of carbon per hectare emitted to the atmosphere in this conversion. If I take primary forest and turn it into cropland, it's even worse. It's 198 plus 25, so 223 tons of carbon per hectare. CO2, you multiply by 3 2/3, it's a lot of CO2, all right? It's like 800 kilograms. It's like 800 tons of CO2 converted per hectare. All right, 800 tons. All right, that's a lot. Okay, it's a huge number. Just think of what 800 tons means. And so the CO2 emission from the conversion of the 1 billion hectares of rainforest into agricultural land itself would put the goals of the Paris Accord, which have been made more stringent now, 1.5 degrees or substantially less than 2 degrees, it would put those out of reach. That CO2 emission alone blows the whole remaining carbon budget. So this is a serious deal. We do not want to do this. It clobbers us on, in other words, if we solve the one nexus problem, by just cutting down tropical rainforest to meet the tropical demand for meat. Then all of a sudden we've got the carbon budget blown for the entire world, and we've got a mass extinction, okay? And this is why the food system is such a big driver of what's going on. Now, fortunately, I don't think that's gonna happen. And the reason is, I think, not because people are gonna change their diets behaviorally, but because they're gonna wanna use cheaper meat substitutes. In addition, it's worth noting that agriculture is responsible for a substantial amount of the greenhouse gas emissions. So the previous slide was about what happens when you make agricultural land, and the carbon that used to be stored in the land goes into the atmosphere. Once it is agricultural land, instead of being a carbon sink the way CO2 fertilized forests are, it becomes an emitter of greenhouse gases. So on top of that conversion, you make more emissions. 1/7 of the greenhouse gas emissions are already due to agriculture. And this is the breakdown. So the nitrogen fertilizer oxidizes to N2O gas, which is a substantial long-lived greenhouse gas. And we kind of need to do that if we're going to fertilize and grow stuff on it. Enteric fermentation by ruminants, that is the anaerobic digestion in cattle stomachs, emits methane. Rice production emits methane. And then there's also energy-related emissions, and those are farmers driving around and you know, in diesel-powered tractors, that sort of thing. Manure management is causing some methane emission and so on. But the big story here is fertilizer and methane from cattle and rice, okay? And so agriculture becomes a substantial player in the global greenhouse gas budget, on the order of the same as transport, all the cars and trucks and planes and ships and stuff, all right? So when you convert tropical rainforest into agricultural land, you cause an 800 tons per hectare CO2 emission. And then once it's established, you cause a substantial ongoing CH4 and or N2O emission. And the fact that the rainforest was absorbing carbon before because of CO2 fertilization is no longer true. So there are 3 ways in which this hurts the greenhouse problem, all right? Oh, and this just shows that because these are yields, these are emissions of different greenhouse gases from agriculture and from forestry and land use. And you can see that most of the CH4 and N2O, although we talk about the CO2 increasing, the N2O is also increasing, and the CH4 is also increasing. Although it should be noted that the methane, atmospheric methane, behaves in a complicated way. It stops growing and then it drops for a little while and then goes up again. We don't actually understand that very well. It turns out that the chemistry of methane in the atmosphere is difficult. Okay, it turns out that the primary way in which it's oxidized is through hydroxyl radicals that are so short-lived in the atmosphere that no one's figured out how to measure their concentration. And so the fundamental inorganic chemistry of methane degradation is not known. This is a useful table. What it shows is the global warming potentials of food in broad categories, all right? So when you consume an amount of food, you can think about how many greenhouse gases were embedded in that food. And you can actually take a mass to mass global warming potential, just the way you can for methane or anything else. And the answer is that it's almost 30 for beef and lamb, but for vegetables, it's half, okay? So what that means is that consuming vegetables means that if you consume a kilogram of vegetables, that's like emitting a 1/2 kilogram of CO2. But consuming a kilogram of beef means emitting 28 kilograms of CO2 or 29. So eating a half-pound steak is like driving 22 miles at 30 miles per gallon. Okay, that's what it's like. One other constraint on the land system, on the agricultural land system, is shown in this slide. At Princeton, we did this thing that is the most widely used guide for the US government in how to get to net zero. And what we did was to plan out as a giant engineering projects, the conversion of our US energy system to one that emitted net zero on a 6-kilometer grid. All right, so it was a cooperative university-wide effort. And it's available online. It's called the Net Zero America Project, okay? And it's got this titanic amount of data that's publicly available. And if you go to the White House and you're in this area, that's the first thing they hand you. You have to like look through this and understand it and stuff. So it's what everybody uses. And this is actually one of the figures from that, and it shows 2050 a build out of biofuels facilities and the biofuels feedstocks that because of it. The punchline here is that in that work, the different scenarios limited how much biomass we'd allow to go into the energy system, so as to protect food security, food prices, and not cause all the forests to get whacked. And whatever that constraint is, the optimal, economically optimal energy system wants all of it. So if we make it 1 billion metric tons of biomass, it uses the full billion. We make it 2 billion, it uses the full 2 billion. So energy wants to devour food production, and it's going to have to be stopped because as it's going to have to be regulated to keep there from being a big problem there. I also have shown this before, their predicted crop yield decreases from climate change. So if we let climate change run amok, then the yield increases we've been talking about won't continue to happen. Water use, this is just to round out the nexus problems. There's a bit of an increase in irrigated area that is forecasted to meet this demand, business as usual demand. That's the dark blue, but it isn't much. And that's because we've already irrigated just about everything we can irrigate. All right. Now here's the clicker question. All right. Have I done everything I need to do? Select. Okay. So consider your personal CO2 emissions caused by, all right, you're going to eat 50 pounds of beef. All right, that's a lot of beef, but you're going to eat 50 pounds. You're going to take your time doing it, obviously, but you said, I'm eating 50 pounds of beef. I'm going to joyride 1,000 miles in a 15 mile per gallon gas guzzler. So I've got a 1969 Hemi Cuda, and I'm going to just drive it around and make noise for 1,000 miles in San Diego. All right. Or I'm going to go to Panama with EEB's environmental studies program. The semester in Panama, if any of you are planning on doing it, I really recommend it. I used to teach coral reef ecology and it's a blast. All right. So it's an environmental study thing. Okay, I think that's enough. Everybody finish up and we'll look at the results. Still kicking along here. We're almost out of time. And the answer is 45% of you thought eating 50 pounds of beef was the biggest. 11% of you thought that, or 10% of you thought that it was joyriding in the car, and 37% thought it was going to EEB's environmental studies program. And the answer is in fact C. Air travel is unbelievably bad. Yeah, I think I'm supposed to, yeah. Those are the numbers. So air travel, you think that, traveling around in a plane isn't so bad because, I mean, there's so many people in the plane. How could it be? And the answer is that that it's like emitting 20 miles or 20 miles or 25 miles per gallon, depending on the plane, driving a car by yourself all the way to Panama, okay, with just you in the car, right? So planes fly by using titanic amounts of fossil energy. And so flying around, it's important just to be humble and remember that, you know, I don't want people to stop flying around and like become insular. And this is one of the reasons why I think what we're going to be talking about next in the next few lectures is how to actually use technology to solve the climate problem. And I think we're going to have to, and not just have behavioral change, unless we want to stop traveling, stop seeing other cultures, you know. And so this just brings that home, right? Even going to a foreign study blows your greenhouse budget, okay?